So we're going to derive the continuity equation from first principles. So I've sketched out our representative elementary volume here. It's infinitesimally small so that numerical errors are minimized. And this is the mass rate flowing into the cell shown here. This is the mass rate out of the cell here. And we said the governing equation is that the mass rate into the cell minus the mass rate out of the cell is equal to the rate of mass accumulation within or inside the cell, right? And so the unit of every term in the equation we derive will be mass per time, which is mass rate. So, starting with the left face, where fluid is going in, how do you compute the mass rate into the cell from that left face? So right now we're only working in one direction, in the x direction. So this is the x direction, right? So this is what thickness in the x direction. This is y direction. So this is thickness in the y direction, and this is thickness in the z direction, delta z. All right. So working in the x direction only, what's the mass rate into the cell from the left face? It's a function of flux, right? And what did I say flux was in the last class? Flux is what? Flux is rho v or rho u. So here it's velocity in the x direction. That is mass flux going into the cell. But what we're looking for is mass rate. And if you look at rho v, which is rho ux, it's in units of what? Rho is mass per unit volume. Velocity is what? Distance per time, right? So length per time. And so this length cancels out the length and the volume, and you're left with area, right? So technically this length precisely is delta x, right? The velocity in that direction is delta x, and this volume is delta x, delta y, delta z. So the area is precisely delta y, delta z. And more graphically, you can see it's this length, right, which is delta y, times this length. That's the area through which the fluid is flowing, right? So we're going to multiply that area by this flux so that the unit now becomes mass per time. Do you see that? So if you think about the unit, it's mass per unit volume, and volume is delta x, delta y, delta z, right? Times the ux, which is precisely delta x per time, right? Times the area through which the fluid flows, which is delta x, delta y, delta z. So this cancels all of this. Sorry, this is delta y, delta z. That's the area, right? Delta y, delta z. So delta x, delta y, delta z cancels delta y, delta z. And what you have is mass per time. So that's your mass rate into the cell. Now, what do you think the mass rate flowing out of the cell will be? Will delta y, delta z change? No. The area remains the same. So the area of this face, the area of the right face is equal to the area of the left face. Correct? Will will rho u x change? Of course, the velocity can change as the fluid flows through the tortuous part in the porous medium. The density can also change because technically the pressure on the right face can be different from the pressure on the left face. So what's the flux out of the cell is going to be whatever went in plus the change in that flux that went in. So the delta of this flux. So this is what you're going to get on the outside. It's what went in plus a change in that flux, right? And then all of this will be multiplied by the area which doesn't change. Good. So the rho, obviously, we already said is the density of the fluid. The U is the volumetric flow rate, right? And these are the thicknesses. So we're going to use our mass balance, which is that mass in, or mass rate in, the rate of flow of mass into the cell minus the rate of flow of mass out of the cell, so mass rate out, equals rate of mass accumulation, which we'll talk about next. But before talking about these, we can express this term using whatever we just derived, right? So it's rho u x delta y delta z minus all of that we'll worry about this later, like I said. And you can see this term is precisely this term. So this cancels out, so this cancels out this, and you're left with only minus delta, right? The second term here is what you're left with. So you're left with minus delta of the rho ux delta y delta z, which is your net flux in and out of the system. And again, we'll worry about the rate of mass accumulation in the next video, because I'm going to stop right here.